I hope you can hear me.
Yes, sir.
Okay, great. Yeah, I've shared my screen. If you aren't able to see it, just let me
It is visible, sir.
know. Okay, okay, great. Okay, so today's question will be based on um, week 7 lectures, which was just, which we are currently into it, not over yet. Okay, uh, so this is the first question for the day. So it's regarding half transforms. So before we even solve the question, can anyone say what is half transform? What is half transform? It's just the last lecture for this week. Yeah, it's just not even the last lecture. It's the last topic for this week. Yeah. Any guesses? At least where is it used?
Model fitting.
Model fitting. Are you sure?
Yes, sir.
Okay. I mean, what kind of models then? If you say model fitting. So, any examples that were discussed in the lectures that you remember? It's finding lines, for instance. If you want to find lines in an image, you can use half transform to find it. And not just lines, but any parametric curve can be detected using half transform, and it's used in images. So, why is it called a transform? Um, okay, if you remember something like this from the class, so first we have image space, which we try to transform it to half parameter space, or is just a parameter space. So for the given case, we'll take that we have points which lie on a line. Uh, so we want to detect this line. So what do you mean by detecting this line? I mean, so we want to find the parameters of the line. So for line, we generally have two parameters. I can take this as M and take this as C. Okay. So what do we do here? So our line is y equals mx plus c. So for every point, we'll see how many lines are crossing. So maybe this one has m1, b1 as the parameters. This has m2, b2 as parameters. Okay. So for this specific in this space, we first try to discretize MNC because we want to deal these things in computers. So we cannot use the continuous versions. Otherwise, MNC are continuous by nature, but we just discretize it for convenience. So once we discretize it, assuming that M1 lies here, for instance. Okay, this is the C1, and maybe I'll just use the notations out here. This is C1 and this is C1 and C2. So M1 and C1 lies here. So this specific block will have plus one vote. Okay. Similarly for M2 C2, if they lie somewhere here, M2 and C2. So now this specific will block will have a vote increased by one. So we'll try to count the number of votes which are gained by each line. Okay. So once we get the count of votes, so get the count of votes for each combination in the parameter space, and then what do we need to find? What's the next step? How are you sure about which M and C to pick for this instance? So for instance, this is M star and C star. This might lie somewhere here. So this will have the maximum votes, right? Maximum number of points passing through this line. Correct? So what does this mean? We need to find the maximum in the parameter space. So this maximum, the location of the maximum gives us what? Gives us what? Gives us the parameters. Is it clear what half transform does?
Yes, sir.
Are you sure? Okay. So if it's clear, then I think this question will be pretty easy for you. So the whole idea is we want to convert things from image space to some parameter space. We specifically call it as half parameter space, and this transformation is called as half transformation. So so it's just a voting mechanism. We try to we try to check for different curves. Here, for instance, it's just a line, so, and we see for the specific parameters how many of the points actually support those that specific curve, and based on that we'll add the count here. Once we add the count here, and once we sweep over all possible parameter space, for here it's the slope and the intercept M and C, we just need to find the maximum of votes which will give us M star and C star, the location in the parameter space. So that's the principle. And if you have multiple lines, then you need to find local maximas. There will be multiple local maxima, and you need to find the I mean, maximas within a specified region. That's all. That's all the idea is. Okay. So based on what you know now, can you tell me is the first option correct? Half transform does not require any discretization of the grid in parameter space. Is it true or false?
False.
Why do you say?
Because at the beginning when they said like we need to discretize the parameters.
Yeah, I said it. That's okay. But what
Yes.
could be the other reasons? to parameter
Then,
to discretize it.
like if we discretize, we can represent it like easy for like computation.
Yeah, it's useful for computation. I understand. Apart from that,
We cannot represent analog in
okay,
computation.
okay, that part is fine. Okay, I mean any other specific reason? Okay, now if I discretize it, so how should I discretize it? Is there any particular way to
Up to some
discretize?
decimal places.
Okay, how do you decide that?
No idea.
Okay, so I'm just giving you an intuitive idea. So if there is noise, right? If there is noise in the image, okay, I'm short of colors. I guess I'll use this. So if there is noise in the image, so this pertains to noise. So if you have noise in the image, then what? Because of these unnecessary points out there, you might find some other. Well, I'll not consider this kind of noise. So some specific. So if you have noise, what I was trying to say, yeah. If you have noise here, then the all of these may not lie exactly on the straight line, right? So it might be slightly shifted here. This one might be slightly shifted here. This one might be slightly shifted here. But all of these actually represent a single line. It's just that due to noise, the points have been shifted. So because the points have been shifted, now you might not get, I mean, maximum vote so easily. So you might get a block, for instance, like this, where you have a set of maximum votes, right? So based on the amount of noise, you want to discretize the parameter space. So if the noise is high, I mean, relatively high, but still you're sure that there is a line out there, then you might want to just increase the discretization width. But if you're sure that whatever points that you detected they lie exactly on a line, then you can even fine tune your discretization space and get accurate M and C. Is this explanation clear? So based on
Yes, I
noise,
got it.
how do you decide on the discretization levels?
Yes, sir.
Okay.
So that M1 C1 and M2 C2 are like, will there be other lines that are like intersecting? So we'll try to find those points, or how is it like?
So yeah, we'll sweep through all M1s and C1s, M2 and C2 in this parameter space.
Okay.
So based on this, I mean, how many points does it cross through? We'll just put the way, I mean, increase the votes for that specific M and C combination, and then we just find the maximum. Okay, so this is wrong. The next one, if the grids are too fine, some points may not be exactly collinear, voting different buckets. Is it right or wrong? This is something that we discussed just now in terms of noise. So if the grid is too fine, then all of these may not vote on the single combination of M and C, right? Fine means this discretization is very small. Coarse means the discretization is very big. So if they are too fine and there is some, even if a small amount of noise is there, then you will not get a proper maximum. Do you agree with that?
Oh, we will get right, sir. Like
Sorry.
if the discretization is very small, then the blue color box will be spread out so that we can find the maximum. Is it like that?
But we need to find. Uh, yeah, yeah. Okay. So, but we only need a single block. We don't need multiple blocks.
Yeah.
So, for a single block, what would you say? So this is true, right? If the grid is too fine, then there may not be exactly collinear voting. I mean, the points may not be exactly collinear, which means that they will vote in different buckets. So that means instead of a single block, you will get multiple blocks which are nearby.
Multiple.
So this is correct. So if the grid is two cores, that means if this grid has the width is pretty large, the discretization width, then there are too many different points in image space mapping to a single bucket. Again, you might not want that if there are multiple lines to detect, right? Do you understand this? So if there are multiple parallel lines, for instance, there are two parallel lines which are very close by. But if your grid is two cores, then both the parallel lines would merge here, right? For a single,
Yes, sir.
yeah. So even this point is right. The fourth one is half transform requires appropriate resolution of discretization of the grid in the parameter space. So that's what we discussed right now. That based on the
Yes, sir.
noise or based on the application. For instance, now if you have multiple lines, you would like to discretize it appropriately. So all last three points are right. Any doubts in this question? So based on this question, I guess we discussed the half transform itself. We'll move on to the next question then. Okay, so we have two probability distributions for four discrete values given as P and Q. Okay, P and Q are a probability distributions. Are you sure that this is a probability distribution, P and Q? How can you say it's a probability distribution?
The sum should be 1.
Yeah, that's right. The sum should be one. For the discrete cases, it's just a simple criteria that if the sum is one, then these are probability distributions. Okay. What is KL divergence? Hmm? What is KL divergence? I don't want the formula. What does it mean?
It gives the difference of how much the two probability distributions are varying.
Yeah, yeah. Yes. So it gives how two probability distributions differ. So based on that, I mean, for both the versions, continuous and discrete, you have different formulas. I mean, one has integral for the continuous ones, and for the discrete ones, we have the summation formula. So we need to compute the KL divergence of P and Q. So KL of P and Q. So how do we do it? It's just simple formula. So here the reference distribution is P. P is the reference distribution. Just for the clarity. Do you think it is symmetric? This quantity is symmetric or not? KL divergence. Hmm? What do I mean by symmetric?
Means if we take reference distribution as either P or Q, then we should end up with the same value, right?
Yeah, if we swap P and Q, the positions of P and Q, we should get the same thing if it's symmetric.
Same. Yes, sir.
Okay, so is it symmetric?
Yes, I guess, sir.
Just see this. Do you think it's symmetric? Just seeing the equation. If you swap P and Q, do you think it is symmetric? It's not symmetric, right?
No, sir.
Do you get the same equation? No. So it is not
No.
symmetric. Okay, so now it's just placing of numbers. So I just expanded this log pi by qi as log pi minus log qi, and then I'll just replace it with numbers. So this is 1 by 4. So log pi all have 1 by 4. So I'll just do this. So this pi I have taken it out. This is 1 by 4, and this is 4 times log of 1 by 4 minus summation over log qi, which is log half.
Sir, I guess your voice is breaking.
Sorry. Oh, my voice is breaking. Is it better now? Hello. Can you hear me? Hello. Can anyone confirm? Hello. Am I audible? Can anyone confirm? Hello. Lakshman, are you there?
Yes, sir, it's now audible.
Okay, okay.
Okay, okay.
Um, yeah. So I just solved this equation. There's nothing much to do. So this turns out to be minus 1 by 4 log 2 to the base e. Well, e, if you know, it's just 2.71. So this thing turns out to be around zero point 0.7. That is 0.69 something. So if you put zero point 0.7, this answer is minus 0.175. I hope this question is clear. I mean, there's nothing much in this question.
Sir, just a confirmation.
Yeah.
Like the last week we discussed about the feature vectors, right, sir? So the feature vectors will be converted into the probability distribution, and then we'll apply this to check the similarity, right?
Yeah. Yes, yes, yes. Yeah.
Yes,
I
sir.
mean, the feature vectors, I mean, you have a collection of feature vectors from which you build a probability distribution.
Yes, sir.
And then based on that, I mean, based on your requirement, you might want to compare the distributions of the feature vectors. That's all.
Yes. So I'm getting one doubt. Like if we like these are like we'll use this to match two images. Like if the or like if one image is having some features, and like if the those features are in the second image, then we are using this to match two images, right, sir?
You're talking specifically about KL divergence?
I know, sir, and about the feature matching.
Yeah, for feature matching, yes. I mean,
So we'll be having some feature vectors in image one, and then we'll be having some feature vectors in image two. So we'll take one feature vector from image one, and then we check the corresponding matching features in the image two. So we'll do like this, like for all the feature vectors in image one, right, sir?
yeah, 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 yes, yes.
Okay, sir.
So yeah, if you, I mean, first for this specific question like KL divergence, you might want to just match the histograms to match the feature vectors, because if you remember, we had histogram of gradients and all, right?
Yes, sir.
The histogram of oriented directions, where the oriented directions, I mean, are the gradients for shift features, for instance.
Okay.
So for given any point in one image and any other, so you want to find the corresponding point in the other image. So you might want to just match their histograms. That could be one
Yes,
of
sir.
the way. Of course, practically it's not done because it's pretty expensive.
Yeah, yes, sir. That's what I was thinking because like there will be a lot of features in both the images, and if we take on comparing from one feature like vector to other feature vectors, then it will take a lot of time.
Yes, yes, yes. So I mean,
Okay,
this scale divergence is anyways not used currently, but you can think of it like that.
okay, okay,
Anyways, this
okay.
specific
Thank you.
question, the next specific question, it's more practical rather, and it's still used actually.
Yeah.
So we have a question on KDT by the way. So we are these points are given in 2D plane, I mean, you have some two-dimensional features, and then you build a 2D binary search tree, and they ask which of the following are leaf nodes. So ultimately, you need to build a 2D tree. With this 2D tree, you want to, I mean, build a 2D tree and then just find what are the leaf. So does anyone remember how to do it? So
Yes, sir. So we'll take the first 3 comma 6.
first we'll take this 3 comma 6, and
Yeah,
what is the reference coordinate that we'll consider here is x.
X. Yeah.
Now next is 1715,
17 comma 5.
where it will lie?
Right side.
Right side. Why?
Because 3 is, sorry, 17 is greater than 3.
Yeah, 17 is greater than 3, so it will lie on the right side. But then again, here we consider the y coordinate instead of the x
Y
coordinate.
core.
So
Yes.
if you have a k dimensional tree in general, so for every level the dimension will change. Dimension 1, dimension 2, dimension 3, up to k dimensions. Again, then you will go back to the first dimension for k dimensions
Okay.
in general. Here it's just 2, so again after 2 we'll come back to 1 in the next level. Okay, the
Yes,
next
sir.
is 13 comma 15. Where should it lie?
Uh,
Come on, 13 means it's greater
right
than 3
of 3 comma 6.
here, so it will come here, and now from here where it will go?
15
15, right?
equal.
So equal means I will choose to keep it at right.
Okay.
So 13 comma 50 will come here. Okay. Next is what? 6
6
comma 12.
comma 12.
Where should it lie? 6 means again it will come to the right
6
side, and
and
12
left side.
means from here,
Left
from it
side.
will go to the left side because 12 is less than 3. Here again for this whole level the comparison will be x. Okay. Next is what? 9 comma 1. 9 comma 1, where should it lie? 9 is again it will come here, from here 1 means it will go here,
Left.
and from here 6 is here, so
Right.
6 is greater than, less than 9. So yeah, so we'll come here 9 comma 1. Again the reference coordinate here is y, so we come here. Next is what? 2 comma 7. Where should it go? Here, right?
Yes, sir.
2 comma 7 reference is y. Okay. And 10 comma 19. 10 means 33, so it will go here. 19,
19. Right.
19 is right, and then again 13, so it will
10.
go to left.
Left.
Yeah, so it's 10 comma 19, right? Yeah. So both of these are on the same level, so the reference is y coordinate. Okay, so we constructed this binary tree, which is pretty simple. So which of the following are leaf nodes? So what are the leaf nodes that you see here?
27911019.
Yeah, all these are leaf nodes. So it is 2791 10.
1019.
Yeah. So is this question clear?
Yes, sir.
I guess this is the easiest one that we have.
Yes, sir.
Okay. Okay. The next question is also easy, I guess. So based on the previous question, question three means this one. This is question three. So now you are given a query feature vector. This is where your matching comes. So from one image you would like to build the KD tree, and from the other image you will get a query feature vector, and you would like to see which feature vector does it even correspond to in the reference image. Okay, so for this, anyways, I'll just copy this. Okay. So we are given the same tree, given a query feature q which is 9 comma 18. Choose the nearest neighbor to q using the Euclidean distance. So that means we just need to take the L2 norm between the query feature and the feature that we are considering in the current node. So which one is the nearest neighbor that we need to find? So first we'll check with this one. So how does it go? 9 minus 3 is 6 square. The distance here will be 6 square plus 18 minus 6 is 12 square. How much? How much is this? 144 plus 36. 180. Write something here. Distance for this node is, maybe I'll just change pen. Okay, yeah. So this is what, 6 square plus 12 square, which is square root of 180. And what about this specific node? This is 7 square plus 11 square, which is 121 plus 49. Square root of 170. What about this? D is square root of 8 square plus e square, 64 plus 9, 73. What is this? How much is this? 30 minus 9, 4, and 18, 15, 16. Okay. 16 plus 9, 25. How much is this? 9 minus 6, 3. And this is 18 minus 12, 6. So this is 36 plus 9, 45. How much is this?
Square root of 2.
Yeah, 1 square plus 1 square. Okay. At least I got one answer.
17.
This is 17. So square root of 17 square. Since we are putting everything in root, 17 is 289, right? 17 square.
Square and square root cancels, right?
Okay, yeah. So I'm just keeping everything square root. That's all. Okay.
Okay, sir.
I don't want to compute now. Square root of 180. So
Yeah.
what is this giving us? So ultimately we computed it for distance with every other feature vector. So in reality we don't do that way. So if you remember, uh, this this KD tree partitions it based on the coordinates, right? So for instance, if you have x coordinate and y coordinate here, based on the first coordinate threshold, it will be here. Threshold in the sense these uh, values at the root nodes can be considered as threshold. So based on this, you can partition it uh, given the values, and given the values, you can select the region. But it might be possible that you have some point here which is closed than some other point. For instance, if this is the query point, and if you are in the current region, which is this is the current region. So it's possible that this distance is larger than this distance. So you generally try to check not just within the regions, but just regions which are nearby in an actual KD tree, and then you can discard these regions. These regions can be discarded because they are pretty far away. Okay, so this is how practically it's done. But for this question, if you try to make this partition of the xy plane, then it will almost turn out to be that you have to check it for every other node. So okay, fine. So given these, what is the minimum distance? Which feature vector matches very closely to the query feature vector q?
10, 19.
Yeah, because the this has the minimum distance. So it's the leaf node in the right subtree 10 comma 90. So right subtree in the sense they are considering this part as subtree. This is the right subtree. That's all. Okay. I hope this question has given some idea about how to deal practically with feature matching.
Yes, sir.
Okay. We'll move on to the next question. Okay. Yeah, this question will check your understanding of transform. In an image, which of the following can be identified using half transform? Parabola? Yes or no?
Yes, sir.
Okay. Why do you say that? When can you use half transform? If you know that, then this question is just a cakewalk. When is it desired that you want to use half transform?
When we want to identify any shapes.
Yeah, shapes. So which can be parameterized.
Yes, sir.
Yeah,
Parameter.
yeah. So for half transform, the requirement is half transform requirement is that you need to have a parametric curve. So what does it actually do? We find the parameters using half transform. That's all the idea is. And so once you know this, so does parabola have any parametric curve equation?
Y square equals to 4ac.
Yeah. So yeah, that's the standard parabola, which is fine. So yeah, it has a parametric curve equation. So this is right. What about hyperbola,
Yes, sir.
ellipse?
Yes, sir.
All these three belong to
Conics.
yeah conic sections. If you remember, we have done this in the first session or second session. Probably
Yes,
the
sir.
first session. Yeah. So what about point? Do you have any parametric form of a point?
No, sir.
Point can be any x comma y, right? We don't
Yes,
have
sir.
any curve in that. So it's just a single point. So we cannot use a point for half. I mean, we cannot identify a point using half transform. What other things that we did to identify points?
Lines. Circles.
No, line circles is fine. That's for half transform. But if you want to identify some key points, what are the things that we did? Key points. I hope you understand what do I mean by key points. That was done in the last week's lectures.
Uh, yeah.
Feature
Edges
detector,
will
feature
form.
matching, all these things come from key points, right?
Yes, sir.
So that key points are those corner-like locations which are interesting to us in some sense.
Yes, sir.
Interesting in the sense that they capture most of the information. They vary in all the directions. So based on that, we call them interesting. Okay. So this one is the next question that we have. Which of the following is true regarding random sample consensus? Okay, what is ransack?
Uh, so if an like sir took example of two dimension, in two dimension, if we consider any 2 points, then we draw a line over it. Like we'll we'll draw a line, like we'll fit a line, and then based on the points that are similar, we'll like based on some threshold, we'll consider some points as inliers, and then we'll like remove all the other points as an out, like we'll consider other points as an outliers, and we'll do this iteratively, and then we'll select the best model.
Okay. Okay, what is it then? You just gave me a full example, which is fine, but what is it? Where do you want to use it? Well, again, it's a model fitting
A model
approach.
fitting, yes
That's
sir.
okay, but when?
Again, when we have some curves,
No, that's okay. But anything else? When to use ransack?
when we have outliers.
Yeah, when data contains outliers. So if you have outliers, then whatever you said makes sense. If everything is fine, then why do you want to use it?
Yes sir.
Yeah. So what you gave, I mean, whatever example you gave is just the line fitting example, but you can use it for any curves, of course. So any model fitting approach, including homography, fundamental metrics, all these are models, mathematical models of the underlying scene, right? How are they transformed? So based on that, you can just use Ransack algorithm. Even for computing the projection matrix, if you're given 2D to 3D point correspondences, 2D means the image points and the 3D means the actual scene structure points. If you're given that point correspondences, you can use Ransack to compute the projection matrix, even in the presence of outliers. So in real data, we do have outliers, right? So
Yes
a
sir.
simple instance is like the marks in exams. So most people will have marks somewhere between X to Y. I would not label it, so let's keep it X to Y. But there are some people who will score really nice, and there are some people who are not able to score. So these are generally, you can consider them as outliers. So these people don't need extra attention, but these people need too much attention, right? So based on detecting outliers, you might want to do something with them. But for the case of computer vision, you might want to just throw it out because they are outliers. That's all. Okay. So I hope the basic idea is clear for what, I mean, when to use Ransack. So what Ransack does is exactly what you said. So if you have data, um, since we are going with the line fitting exercise, we'll just go ahead with that. So I'll just put outliers on the one side of line. Okay. So now if I try to put a line here, including outliers, so it will look something like this. This is line with outliers. So I'm fitting it with mean square error. Fitting line with, this is an example, mean square error. Mean squared error. So what does mean squared error means? So if you have error for every point, ith point, this is error for ith point, then what does it do? So our final error is just the summation of each of the errors over all the points. This is the total error, which is mean squared error, MSC. Okay. So when I blindly take all the points, then what does it happen? Because these errors are high, so to compensate for these errors, um, our line shifts. Our line shifts this way, right? But now, if I only consider inliers, so this is line with inliers. here I should write outliers and inliers. So this unnecessary uh, what do you say deviation from the original line is created because of the outlier presence of outliers. So once you detect the outliers, what can you do is you can just remove them and fit the rest of them, which is what is done in the last step of the ransack. So what ransack does is choose any 2 points. So for choosing points, I'll use green color. So first I'll choose these 2 points, and based on this, I'll fit a line, and you see how many points are there within some threshold. If I have some threshold like this, so based on this threshold, there are only 3 points out here. But now if I choose another set of points, how many colors do I have? Okay, fine. I choose these two set of points and now create a threshold out here, and based on this threshold I get 4 points. So with this we can conclude that these 4 points are inliers and these 2 points are outliers. So given these 4 points, now we'll fit a line ultimately. So that's what is the basic idea of ransack. So in general you just want to detect outliers for any model and then throw them away, and with the remaining inliers you just do a model fitting, usually with mean square error. Okay, so given this idea, can you now answer this question? The key assumption of ransack algorithm is that the maximal consensus set must contain no inliers. Is it right or wrong?
Wrong, sir.
Yeah, because it should contain all
Ah,
inliers, not no
all in
inliers.
layers, yes,
Or
sir.
like no outliers. That's what we want,
Yes,
which is wrong.
yes.
Okay, the next one is ransack is a parallel hypothesizing and testing algorithm. Yes or no? So I hope you understand the hypothesis part. The hypothesis part is I am first I'm assuming that these 2 points are the correct points, and then I fit a line. So that's my hypothesis. And then test how many points lie within that threshold. That's the testing part. So again here in this case this is another hypothesis that I choose 2 points. That's my hypothesis that it's the correct line, and then again test whether how many points are there within the line. So is this a hypothesizing and testing algorithm?
Yes, sir.
And what about parallel? Can this be parallelized?
No, sir.
Why?
Because after we finding the once we fit the line only, we'll check the main difference between the other
No,
points.
but okay. So you can parallelize the hypothesis part, right? For every hypothesis part, I can choose one core of my processor to work on it.
Yes, sir. Yes,
So
sir.
in that sense, it is parallelizable, right?
Okay. Yes, sir.
So you can have multiple hypotheses at one point of time and then just push it through CPU cores. Nowadays, you can also
Yes,
use
sir.
GPU. Based on that, you will get multiple outputs in shorter span of time. So you can actually
Yes.
parallelize it. So it's a hypothesis. I mean, it can be parallelized if you want. Okay.
Yes, sir.
So it is an algorithm for robust fitting of models in the presence of many data outliers. Is it right?
Yes, sir. Because we use ransack when
Yeah,
there
we
are
use Ransack.
outliers.
That's the whole point. I mean, we use Ransack only when there are outliers. Otherwise, there's no point.
Okay.
Okay, so a
Yes, sir.
general thumb rule is that if the outlier percentage is more than 50%, then it may not be effective. It could be
So if
effective.
it's
Depends
that
on the.
case,
Yeah, sorry.
if it is more than 50% like that, then the whole thing would be also considered as an important thing, right, sir? If there are many points in the uh, if there are many points within that line, then it it
Mm-hmm.
contributes to a line, right, sir? So,
Yeah, 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 yeah.
oh,
So it depends on the outlier distribution, specifically speaking. So
okay,
So just a thumb rule that 50% is good enough, but if your outlier again makes some other weird kind of curves, then you might satisfy that instead of your original curve. So all those are pathological cases. I'm just talking to you in general. That 50%
Okay,
is
sir.
the general threshold that we would like to keep. So
Okay.
C is also correct. What about D? Oh, it's talking about the threshold. The key assumption of Ransack algorithm is that the maximal consensus set must contain 50% outliers and 50% inliers. No.
No.
Yeah, it should contain less than 50%. Yeah. So this is wrong. So I hope this part is pretty clear to you. We'll move
Yes,
on
sir.
to the next question. Okay. Finally, we got some question which has some maths. Okay. So assume that we are fitting a circle. Okay. Fine. How many minimum number of points you need to fit a circle? You need to fit a circle. What is the minimum number of points required to fit a circle?
2.
Oh, are you sure?
The radius and
No, 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 no. Minimum number of points to fit a circle. How many parameters do you need to actually define a circle?
3.
Three, right?
Yes, sir.
So how many and and okay, what should I say? So each x comma y will give you how many equation? Each x comma y will give me one equation, right? Which is this one, whatever you see, right? This is just one equation, right?
Yes, sir.
Yeah. So we need how many of these for three to get three equations? So we need 3 points.
3. Yes, sir. 3
Yeah.
points.
Okay. So if you see geometrically, if I give you two dots, I can have so many circles. I can have this circle as well. I can have something like a straight line as well, which is almost a circle, but with infinite radius. So yeah. Anyways, this looks clumsy. I guess. So we need at least 3 points to define a circle. So here we are fitting a circle, and we are assuming that 50% points are outliers. So what do you mean by 50% point as outliers? So our outlier ratio, if I go by the notation of the class, is 0.15. Okay, this is the outlier ratio. The next thing is how many random samples of 3 points. See, they took 3 points. That means they are the sample set will consist of 3 points. So our S is 3, which is the sample set are needed to detect the circle with 90% probability. So again, this probability is 0.9, which is the accuracy required. So do you remember that weird formula that was given in the class, which is not weird at all, by the way. It just looks weird. So we'll try to derive it. So the probability that all samples are inliers is what? What is this probability? Given that you have outlier ratio E, that means each sample can be outlier with 15% probability. So for each sample to be inlier, what is it? 1 minus E, right?
Yes, sir.
And each sample within that sample set to be inlier, so we'll multiply it by 3 times. For I mean in general, we'll multiply it S times. So probability that all samples are inliers is 1 minus E whole to the power minus S, whole to the power S. Okay. So with this, what do we need? Probability that at least one sample is outlier. How do I get this?
1 minus 1,
1 minus.
the 1 minus e power s.
Why do you say this? Because
At
these
least
this
one
is just
sample.
a negation, right?
Yes.
This statement is just the negation. I'm just writing it in English terms. So all samples are inliers means if you negate it, at least one sample is outlier. That's what we say in English. So this
Yes,
probability
sir.
is 1 minus of the one that we got earlier. Okay. So what's next? We have to probability that all n trials have at least one outlier, which is what? One sample set. N trials means what do you mean? Probability that all, what do you say? All n sample sets that you have chosen will have at least one outlier. What will it be? It's just this multiplied n times, right?
Yes, sir. N times.
So we'll raise it to the power n. Okay, so we have this probability. So what if I negate this statement? What will be the negation of this statement?
Probability that all n trials have, like, all are in layers.
No. See, all means at least one trial. So you can replace all with at least, and at least means all or, and depends on how you are defining this as zero. So here we have at least one outlier. If you negate it, we have zero outlier. So we have here that all n trials are corrupted. So we want that at least one trial is not corrupted. This is how the negation works here, which is what? 1 minus e to the power s whole to the power n. So this probability is p, which is what is the accuracy required. So what does it even mean? So if we have at least one trail in which all of them are inliers, that means we'll get, for that trail we'll identify all the outliers correctly, and we'll have maximum consensus. That means maximum points are uh, agreeing with the model which was chosen by this one trial, right? So once we
Yes,
have
sir.
maximum points choosing with that one, I mean that hypothesis, which means that we got our inlier set. Once we got the inlier set, we'll just throw away the inliers, and then we will just find the model estimate based on those inliers. That's all. So that's all the whole idea is. So that's how we derived this whole equation. Now if we just want, we can replace this. Okay. So in our question we need to find n. How many random samples n are required? Okay, so we need to find n. Okay. How will it find n? We just take log, right?
Yes,
Log,
sir.
n will be log of 1 minus
1
p
minus p.
n. Yeah, so here there will be log, which will turn out to, which will come here in the denominator. Is this clear? So this thing will be here, right? Log of 1 minus e to the power 1 minus e to the power minus s whole to the power n. That n we
Yes, sir.
just pulled it down, and then this comes in denominator. So p is zero point 0.9, so which gives us zero point 0.1 here, and this 1 minus e is 0.85, and s is 3. If you try solving it, it will turn out to be 2.41 something. So the minimum n will be n required will be a ceiling function of this, because you cannot do 2.14 time trials, right? Ceiling means you just go to the next integer. 2.41, you do the ceiling function, which is 3. Okay, so answer is 3.
Is it always a ceiling, sir?
Yeah, yeah. So you
Okay.
want to be sure that you are at least you're getting your uh, I mean you're getting your model with this much percent probability, right?
Okay.
You want to be sure that you have this much percent probability. If you take 2, the probability will decrease.
Decrease. Yes, sir. Yes, sir.
Yeah, so we want it to take the I mean we want to take the ceiling.
Yes.
Okay, what more is there? Let me see. Oh, nice. So this is a nice question in the sense that it will test understanding of this week's lectures. Okay, the broad idea. Hmm. So which of the following are examples of model fitting given some data points? Calculation of epipoles in stereo images. Is it a model fitting problem? Yes, no.
Yes, sir.
Why? Why do you say that?
Uh, because we can use like we'll be using fundamental matrix, and so there are parameters that can be.
No, no, no. Don't extend beyond what's given in the question. It's just given that
Okay.
calculation of epipoles in stereo images. That's all. So for calculating epipoles, you need two corresponding points and some transformation, which is yeah, fundamental matrix is fine. So otherwise, what else can you do? If you're given two lines in the second plane as well, image plane as well, you can try find the epipole in the second plane. So there are multiple ways in which you can find epipoles. Given
Yes,
points
sir.
in one image and image one and image two, or else given lines in image two, or things like that. So once you're given those things, it's just a matter of what applying the formula, right?
Formulas. Yes, sir.
So there is no model out there.
Model. Yeah. Yes, sir.
So it's just a formula based question. So we are not estimating anything. It's just computation.
Yes, sir.
So here the question rises of estimation versus computation. So this is just a matter of computation, by the way, since you have the formula. So this is not a model fitting problem. What next? We have an homography matrix given pixels in two images of the same planar scene. Okay. Do you think is it a model fitting problem?
Two.
Yes, no?
Yes, sir. Again, like we can take some point correspondences and then we can form equation and
Yeah, you can form equations, and based on that, you need to estimate the homography matrix. It's not
yes,
computation.
sir. Estimation.
So here the problem is of estimation. Okay, so this point is right. And yeah, it might contain outliers because you have similar scene points spread in both the images. Okay,
Yes, sir.
so the next is given a set of 2D points fitting a straight line or parabolic curve or circle. Is it a model fitting problem?
Again. Yes, sir. Because we'll be estimating the parameters.
Yeah, we are estimating the parameters. Okay. Essential matrix evaluation between corresponding points in stereo images.
Yes, sir.
Yeah, exactly. Again, we are estimating parameters. We don't have a
estimating it.
formula for that. So given data, we are estimating here. Given data, estimate parameters. So that's where the model fitting problem lies. Here, we do have data in some form or the other, but there is no estimation point. So given some specific data like line or homography, things like that, a fundamental matrix, you can just calculate the repose or even the projection matrix that you have seen. Okay, so hope this session was slightly useful. We have crossed
Yes,
halfway.
sir, it was very useful.
We have crossed halfway of the course. So, well, actually more than that. It's week 7. Yeah, we just have
Yes,
5 more
sir.
weeks left. Hopefully, you are able to understand computer vision to some extent. Yep. Any questions on this today's session? Okay, I guess there are no questions. Then I'll stop recording.